You will not
I'm Chris Smith. I'm a researcher in the Department of Physics and a junior research fellow at Somerville. And I've been deputised for the next hour or so to tell you about a project that's taken over my life in the 3 years I've been in Oxford. The project is called Galaxy Zoo, and it's the world's largest scientific collaboration. It involves about 250,000 people distributed around the world, helping us with a fundamental problem we had, which is that we simply had too much data, too many, in this case, images of galaxies for us to analyse. And so we think of this as the first of a new breed of what we might call citizen science projects that don't just involve people like me talking to the general public and to non-scientists and to ex-scientists about what we're doing, but involve working in a real collaboration with large numbers of members of the public. So let me see if I can make the lights a little more civilised. That way you can go back to sleep in polite silence. Hang on, that allows me to sleep if I do that. Never mind. Hopefully that's okay, you can see the slides. What I thought I'd start off by saying, because we will be talking mostly about this one project, Galaxy Zoo and astronomy, is that in some sense, astronomy among the sciences has always relied on the efforts of amateurs to do what we professionals cannot. One particularly famous example from early in the 20th century involves this man, Will Hay, who might be familiar to some of you. I'm afraid it's a little before my time. I had to do some research. Will Hay was a musical and film star, but he was also a very serious amateur astronomer, seen with his telescope there, and he discovered a spot on Saturn, a tropical disturbance, in fact, in the planet's atmosphere, which went on to become extremely prominent back in 1930. And that sort of thing still happens today. For example, this is an image of Jupiter from earlier in the year. This is June, I think, taken by an Australian amateur called Anthony Wesley. And the sharp-eyed among you will have noticed there's a black spot up at the top of the giant planet here. And this is in fact an impact site. In early June, something, and we don't know what it was, it could have been a comet or an asteroid, smashed into the upper atmosphere of Jupiter, destroyed itself, and what you can see there is literally soot, carbonaceous particles which have been thrown up into the upper atmosphere. And as soon as this was discovered, every professional observatory on Earth pointed its mirror at the planet. In fact, this was the first target for the newly refurbished Hubble Space Telescope. But we only knew it had happened because of the efforts of amateurs. So there have always been these, sorry, have I forgotten to... Yeah. Sometimes you actually need a rocket scientist. Thank you. Very quickly, that was a lot, if any of you were relying on the mic, that was a long introduction, and now we're talking about amateurs looking at Jupiter. You can now go back to sleep. So the point was that for tasks involving monitoring things that might change, you need somebody with dedicated telescopes. And we can't afford, as professional astronomers, to point, say, the Hubble Space Telescope at Jupiter every day just in case something might happen. What we rely instead upon is a whole group of amateurs to do the monitoring for us. And if you go further back, of course, the distinction between amateur and professional starts to blur. For example, this man, William Herschel, is probably the greatest English observer of all time, the discoverer of the planet Uranus, but made very little money out of his astronomy. What he was a professional musician. There's a wonderful record of him meeting Handel, the composer, and you think, you can go off in enormous flights of fancy about what these two great minds must have had to say to each other. Handel was writing the creation. Herschel was talking about star formation. You can imagine the conversation. But unfortunately, from Handel's diaries, we know all they talked about was the amount of money that you could make by writing for local churches. So he was supporting himself as an astronomer, and himself and his wife, in fact, Caroline Herschel, were in their spare time doing astronomical observations. And this is one of the more significant results. I know it doesn't look like much, or perhaps looks like an early biological drawing, but this is a map of the galaxy that Herschel made. he had the idea that all he had to do was count the stars in each field he could see through his telescope across the sky, and then that would give him a map of the galaxy. In fact, the method's complete rubbish. What you actually map is the dust distribution. You can't see the edge of the galaxy with the telescope he was using, but you get the idea that the galaxy is a disk, and that's genuine. There are more stars out here than up out of the plane. He placed us at the center. We're actually displaced, but that's not too bad. And in fact, if you follow the theme of trying to establish that there are other galaxies onwards, I think the ultimate amateur telescope is this one. This is a remarkable device called the Leviathan of Parsonstown in Southern Ireland, not your natural choice for an astronomical observatory. It has to be said, the weather is terrible. This was built by the Earl of Rosse, who hit upon the idea, he was essentially making a lot of money out of steel manufacture, and he cut a deal with his workers that they could have an extra day a week off if they spent half of it constructing what was the world's largest telescope. It's a very clever design because he realized that the hard thing with a telescope is enabling producing a mount which lets you swing around the sky. The Earl of Rosse realized that if you have the largest telescope in the world, you're not going to be short of things to look at. And so this telescope can't really swing from left to right. It can only go up and down, supported by these giant walls. And he just waited for objects of interest to pass across. Very, very, very clever. At the time, the big debate was about how many galaxies there were. Obviously, we were sitting in what we know as the Milky Way. But the question was, are the diffuse patches of light that they could see around the sky, are those other Milky Way-sized things at a great distance, or are they just gas? Are they nearby patches of nebulous material? Of course, we now know today that many of them are distant galaxies. This is a particularly nice example. This goes by the romantic name of M51. Astronomers, this will be a theme, should not be allowed to name anything. I was giving a talk the other day about a newly discovered rocky planet around another star. And you can imagine this being another world with a surface we could stand on, and it goes by the name of Crow 7b. We need some help, I think. Anyway, so this is the modern image. What I wanted to show you was Ross's drawing of this object, which we can superimpose with any luck. There we go. And not only is it pretty accurate, but the important thing at the time was that it shows the spiral structure, and he also was able to resolve individual stars. And so by seeing that some of these nebulous patches were made up of stars, he greatly increased the size of the universe that we were considering. Suddenly, not only do we have one spiral galaxy with 100 billion stars in it, but we have many, many galaxies. So these are all amateur results in some sense, but clearly they're expensive efforts. Whether we're talking about Will Hay, who funded his observatory through the proceeds from his music hall career, or whether we're talking about the Earl of Rosse subsidising his work in the manner of the Victorian grand amateurs, or indeed whether we're talking about people like Anthony Wesley, the discoverer of that spot on Jupiter today. We're talking about people who are putting a large amount of time, effort, education into taking part in science. They may be amateurs because they happen to do other things, but they're operating on a professional scale. So one of the things we were interested in was trying to find a way to lower the barrier of entry to science, to doing science, not learning about it. And that's something that I think our project's achieved. But before we get on to that, let me set up the ridiculousness of the situation that we found ourselves in. Never mind the Leviathan, it's entirely the fault of this telescope. Here, this is the Sloan Digital Sky Survey Telescope in New Mexico. It's what happens if you let particle physicists build you a telescope. It was built primarily by a team out of University of Chicago and Fermilab when they decided that they should get involved in astronomy as a way of expanding the lab's activities. Now, a traditional observatory operates as follows. Most of the astronomers in the world will spend a lot of their time writing applications to use telescopes. For example, we've just had a whole round last week when I was applying to telescopes in Spain, in Arizona, and to use the Hubble Space Telescope. Typically, a professional observatory will be oversubscribed by a factor of about 10 to 20 from sensible serious proposals. So a committee will select from among those proposals, and you are very grateful for the few hours that you get. 2 hours on the Hubble Space Telescope is immensely valuable. I've seen a PhD thesis written entirely based on the results of 37 minutes on an X-ray telescope. So we're very grateful for what you get, but you turn up having had to travel to horrible places like Hawaii in the process. It's tough, but somebody has to do it. In fact, the last time I was there, the weather was so bad we didn't get up the mountain. I had to spend a whole week on the beach, but it was horrific. And then I got to go back as well. Anyway, you turn up and you make the most of every single second. You point only at the objects that you've carefully justified in the observations of, and you do not waste any time. Then the next person comes in and you hand over and so on. Sloan is different. Sloan is more of an experiment than an observatory. A group of people got together and decided that all they wanted was an image of and a position of about 1 million galaxies. And they would worry about sorting out the wheat from the chaff, from doing the statistics and so on later. So Sloan just literally scans across the sky, allowing galaxies to drift across its electronic camera, imaging each one for a total of about 2 minutes. And it did this for 7 years, producing, in total, images and positions of about 1 million galaxies. And so what that gives us is our first proper map of a large chunk of the local universe. Now, 1 million galaxies is an insignificant fraction of the whole. We think in our observable universe there are about as many galaxies as there are stars in the Milky Way, so 100 billion galaxies. But 1 million is enough that we're sort of on the largest scales on which we expect anything to happen. We think that if we took this chunk of 1 million galaxies versus another million from over here, or another million over here, or another million over here, they'd look roughly the same. Obviously, you'd have different patterns, but the statistics and the structure would look much the same. So let me plunge you into darkness for a second, because these results are actually worth it. I'm going to show you an early release from the Sloan. We're going to start on the Milky Way, and then we're going to move outwards away from our own home galaxy throughout the Sloan. And we're looking at an early release, so this is about 500,000 galaxies, so about half of the complete survey. And something interesting happens. We start on the Milky Way and we move outwards, and I know this looks like every science fiction film you've ever seen, but this is real data, galaxies in their correct position. And somewhere around now, something interesting happens. You start to notice that the galaxies aren't scattered randomly through space. Ignore the stripe down the middle, that's just an artifact of the direction in which we're looking. But you can see there's a sort of honeycomb structure emerging. In fact, on the left there, you can see there's a bow-shaped feature running about halfway down the image. That's the largest structure we know of in the universe. It's called the Sloan Great Wall, and it's 2 billion light years across. For those counting, that's about 10 to the 25 meters. It's an enormous thing. And on these scales, you find that the galaxies aren't smoothly distributed. This is apparent color, so they're getting red here because of the effect of the expansion of the universe. But we'll stop in a second and rotate our three-dimensional map of the local universe. And you'll really get a sense of what we call this cosmic web, this honeycomb structure. And what we'd like to do is try and make sense of this diversity of structure that we see. We're going to zoom outwards. And this is now going to put the Sloan in context versus the edge of the observable universe. So the axis here is light travel time. And you can see that actually we have a fairly insignificant chunk of the observable universe measured, but it's good enough for most purposes. I'll let that keep running in the background. We end up in the office of the people who made the animation, I think. So what model can we use to try and understand this? Well, in some ways we think we've got the basics sorted out. We start with an expanding universe, in this case contained in a Chicago office, I think. But we have an expanding universe, which began in, or at least was in a hot, dense state 13.7 billion years ago. And we actually know that number more accurately than we know the age of the Earth. So if there are any geologists in the universe, I think you should take any geologists in the room. I presume there are some in the universe. I haven't observed any recently, so I'm not sure. But if there are any geologists in the room, please take that as a personal challenge. I think it's a disgrace that we know the age of the universe better than we know the age of the Earth. Anyway, we have this idea of an expanding universe, and the evidence for that comes from the work initially of Edwin Hubble over in California in the 1920s, really. And this is his original data plotted on a modern axis. So you can think of this as millions of light years. This is kilometers per second of recession, because we see all the galaxies receding from us. Each dot is a galaxy. If you're an economist, this looks like a perfectly straight line. To an astronomer, this is pretty good data as well. To anyone who worked in a science where it's easy to do laboratory measurements, here's the modern version from the Hubble Space Telescope. And we now have hundreds of millions of light years covered, tens of thousands of kilometers per second. And we have this apparently very strong but hard to explain relation that the further away a galaxy is, the faster it appears to be receding from us. And it's this one fact that gives us the idea that space is expanding. To see why that follows as a consequence, the only way I can ever get to this is to think about this painting. This is by the Dutch artist Escher. He was as bad at naming things as astronomers are, so this is called cubic space division, because it divides space into cubes. But what I want you to imagine is that we're all sitting down here on this cube in the bottom left, and that in this universe that we find ourselves in, all of the rods are expanding at some constant rate, let's say 100 miles an hour. So how would that look in this strange universe? Well, the first thing is that obviously all the cubes would appear to be receding from us. We would deduce that we were at the center of the expansion because all the cubes were rushing away from us, but so would anyone on this cube, or this cube, or this cube, and so on. So we'd see all the cubes receding from us. And in fact, we'd see this one up here heading in that direction at 100 miles an hour, just because of the expansion of the rod joining us to it. Now, the one in the top right would be heading in the same direction, but would appear to be receding twice as fast, because this rod is expanding, and so is the rod up there in the top right. So it would appear to be receding at 200 miles per hour. So if you were careful and you did your observations of these other cubes, you'd conclude that the further away a cube was, the faster it was receding from us. It's trivial. It's just because there are more rods joining us to the distant cubes. Now, if you replace the cubes with galaxies, and instead of having rods expanding, you have space expanding at some constant rate. So for every chunk of space, it expands at a particular velocity. Then you have the idea that the more distant a galaxy is, the more space there is between us and it, and therefore the faster it will be receding. We can recover Hubble's law just by letting space expand. We can also, of course, run this movie backwards in our minds. And instead of having expanding rods, as you go back in time, the rods are contracting, and you quickly get back to a point where all the cubes are crushed up on top of each other. This moment that we call the Big Bang. And we can talk about what the universe would have been like back then. In fact, for reasons I don't have time to go into, we can actually measure tiny fluctuations in the density of the universe back then. We think that it was pretty much uniform, but there were tiny fluctuations on the order of a few parts in 100,000. Places that are slightly more dense than the average, and places that are less dense than the average. And it's these tiny fluctuations that become exaggerated to produce the cosmic structure that we saw in the Sloan movie. And I can show you that with a computer simulation. So, for example, we start the simulation 300,000 years after the Big Bang. We run forwards to 15 million years, and we stopped it here. So where you see bright patches, these are regions that are more dense than the average. Where you see dark patches, these are regions that are less dense than the average. And so you can predict what's going to happen. We've got a small blob here, maybe 1 part in 1,000 more dense than this part, the dark patches to either side. And so any material nearby will feel the gravitational pull of this blob and tend, on average, to move down into the denser regions of space. And that has the effect of exaggerating these tiny fluctuations. So the rich get richer, the places with more stuff have a stronger gravitational pull in more material, and what starts as quite a smooth field from 15 million years to 1 billion years to 5 billion years, and then to today, becomes quite exaggerated. We have this web structure that you saw in Sloan. You can see it much clearer if I run it forwards as a movie. Taken out the expansion of the universe to make it easier to see, but you see what starts off as a smooth distribution of matter ends up as this cosmic web. And so, in some sense, this model provides an explanation for the structure that we saw. You can pretend that you were sitting in the center of this cube and had a telescope like the Sloan, and you can ask how many Milky Way-sized blobs there are in your field of vision, what the largest structure you should expect is, how big the biggest voids, the areas without any material in, are, and so on. And we get the answers pretty much right. On a large scale, we understand the formation of the structure that we see. So in some sense, we're done. Modern astrophysics is finished. We have a model that fits. I don't get to go to Hawaii anymore. Don't tell, I know the head of Department of Physics, Roger Davies, is coming later. Don't tell him that I said we were done. I still want to go to Hawaii. But in another sense, the model that we use is profoundly unsatisfactory. Because to get this right, the recipe I put together for the universe is a little distressing. So let me show you. This is a pie chart that splits the distribution of the universe's energy, its energy density today. And 0.03% of the universe's energy density is in the form of what an astronomer would call a heavy element, a metal, anything other than hydrogen or helium. So to an astronomer, carbon, oxygen, nitrogen are all metals. It drives chemists absolutely up the wall. So 0.03%, everything we actually care about as humans, our planet, everything we're made of. 0.3% is in the form of fast-moving particles called neutrinos. 0.5% of the universe's energy density is in the form of stars. So we're deceived by looking at the night sky with our eyes. We see these wonderful sparkling things that pick out the shapes of galaxies, and yet we don't realize that we're only looking at 0.5% of the universe. What's the rest? Well, 4% is in the raw materials from which stars could form. Hydrogen, helium, gas, which probably will eventually go on to form stars. So that gives us a total of about 5% of the universe in forms that we understand. The rest, 95% of the universe, presents a profound problem. 25% of the universe's energy density is in the form of something called dark matter. This is stuff that has gravity but doesn't interact with light, and we infer its presence indirectly. For example, if I don't put dark matter in, then the process of exaggerating these tiny fluctuations happens much slower, and we end up with a universe that's too uniform today. We also need dark matter to hold spiral galaxies together. We can see how fast the galaxies' disks are rotating, and without the presence of a lot of about 6 times as much matter as we can see hidden there, the galaxy would fly apart. So 25% of the universe is in this form of dark matter. We blame the particle physicists. They need to discover a massive neutral particle. And then we need to say that there are 6 times as many of these as there are ordinary atoms. They tell us this is feasible. Hopefully the Large Hadron Collider in CERN will produce some candidates for this dark matter. So it's embarrassing, but between friends I think we can get away with dark matter. The real problem comes in the other 70% of the universe's energy density, which is in the form of something that goes by the hideous name of dark energy. When this was discovered, so this is a 5th fundamental force. So we're used to, as physicists, explaining everything via 4 forces: gravity, the electromagnetic interaction, and then 2 nuclear forces. However, we discovered in the late 90s that, much to everyone's surprise, the universe's expansion is not slowing down, but is speeding up. And none of the 4 forces can possibly be responsible for that speeding up of the universe's expansion. So we have to invent another force. And we call it dark energy. The British astronomers involved wanted to call it quintessence, which is nicely classical. It was the fifth element of the Greeks, the fifth force. The Americans named it, and they called it dark energy. And the rumor is that it was because they wanted to try and get funding from the US Department of Energy by claiming that 70% of the universe's energy is in a form that we can't even understand, let alone tap. A maneuver that's proved remarkably successful, it has to be said. Anyway, the point is that we have no idea what form this force takes. We don't know how it behaves. We can measure its strength today, but what we need to do, if we're going to understand the fate and the composition of the universe, is look back and see whether it's changed, how it's affected the formation of galaxies and the universe we see today. Now, to do that's hard, because if we just compare the simulation I showed you to the observations, I said we get all the answers right. So how can we get more information out of these simulations? How can we produce new challenges to the theoretical model to help us look for places where we can get information about dark energy? Well, one way to do that, and this was the inspiration behind Galaxy Zoo, is to realize that I've pulled the wool over your eyes slightly when I say that this simulation matches that beautiful fly through the universe. I turned the lights off for the fly through the universe because it's worth it, whereas this is just blobs. All this simulation knows about is the behavior of matter. It doesn't care about star formation, doesn't worry about chemistry, it doesn't worry about producing galaxies that actually look like galaxies. Things like this. I said it gets the right number of Milky Way-shaped sized blobs, not the right number of things that look like the Milky Way. So one way to interrogate these simulations is to say, okay, we know we have spiral galaxies and we have elliptical galaxies. We have merging galaxies and we have warped galaxies. We have all sorts of things. So if I can record in the Sloan where the spiral galaxies are, suddenly my computer simulation needs not only to get the behavior of matter right, it needs to get the history of star formation right, it needs to get the history of galaxy interactions right. It becomes a much more stringent test. All we have to do to impose that test is to classify the galaxies that we have in the Sloan survey. Sorry, there we go. So luckily, there's a well-known classification scheme, Edwin Hubble again. He called it the tuning fork diagram. And essentially, it splits elliptical galaxies from spiral galaxies. He thought it was an evolutionary sequence. He thought you started off here, the gas cloud collapsed into a disk, which then formed spiral arms, and then the arms wound themselves up. That's complete rubbish. But it turns out this division is quite profound. It tells you about the dynamic state of the galaxy. So elliptical galaxies tend to be more massive. They tend to have formed stars earlier. They tend to have been formed from collisions of galaxies, whereas spiral galaxies are homes of most of the star formation in the universe. They tend to be solitary. They live in different parts of the universe. This division is as fundamental as that that you've come across as a medical researcher trying to understand the behavior of a disease without realizing that humans come in two flavors, male and female. You absolutely need to know what galaxies you're dealing with. The only problem is that we have 1 million. In the 50s, when the largest sky survey was a few hundred galaxies, professors would deign to classify galaxies. And there are big atlases published telling you that Professor whoever it was thinks that this galaxy is a type E4b subclass 3 spiral, elliptical. In the 80s, we're up to thousands of galaxies. And that's fine, because you can get a grad student to look at 1,000 galaxies. With 1 million, it's rather difficult. And we needed to look for new ways to do things. So one way to do this is to use a computer program. That's expensive. You have to run it locally. And it has a more fundamental flaw. Computer programs will get 70 to 80% of the galaxies right, which sounds pretty good until you realize that the 20% they get wrong are selectively the unusual ones. And they're the ones that contain a lot of the information. So all you find out from computer programs is that most elliptical galaxies look like this, and most spiral galaxies look like these. Well, that's fine, but we want to find and correctly classify the 20% that tell us more about this border and tell us more about the formation of these things. So we couldn't use a computer program. What we did know about was a program called Stardust at home. Now, Stardust was the spacecraft you can see up there on the right that flew past this potato-shaped object. This is Comet Wild 2, the nucleus, and had this amazing detector made of aerogel, the lightest material that we've ever created. And the aerogel would capture particles from the comet. And then the spacecraft returned to Earth. It landed safely. And what you ended up with was, if you take a thin section of this aerogel, you can see here there's an entry point, and then there's a track, and then there's a dust grain sitting here. And they had something like a couple of million dust grains. If you want to study the comet, that's fine. You can take a random sample. Amongst those millions of dust grains, they thought there might be 10 or so that came from beyond our solar system. It's a chance to get our hands on pristine interstellar material. The only problem is that you have to decide which 10 they are. You'd like to take them all out and look at them all in the lab, but the procedure to extract the dust grains is complicated and expensive. So instead, they needed somebody to review pictures like this and look for things that are unusual. And they put this on the web, and 20,000 people spent a lot of their spare time looking at dust grains. So we knew about this, and I thought, well, surely if people will look at dust grains, they'll look at pictures of galaxies. So we created the Galaxy Zoo website. You turned up, you took a test. I know 6-year-olds can pass the test because they've emailed me. I know at least one professor of physics who failed it, so I think we got the level about right. And then you get a galaxy, drawn randomly from the million, and a set of buttons. Is it an elliptical or a spiral? If it's a spiral, tell us which way the arms are rotating. There's also a star button and one for merging galaxies. And this was launched in July 2007. We actually launched it on the Today programme. We got followed up by the BBC News website. If you've ever seen the BBC News website, has a little applet, a ticker that tells you which stories people have emailed to each other. So on launch day we were there, we were second. Scientists seek galaxy hunt help. Just behind man flies to wedding a year early. Some news is really important. We were still there later in the day, just behind huge dog is reluctant media star. And to my eternal regret, I didn't click on that, so I've no idea what that story was about. But if anyone remembers from 2 years ago, please let me know. The effect was slightly stunning. This is our performance in the first 2 hours since launch. A couple of things to notice. You'll notice there aren't really any classifications in the first 12 hours or so. This is because the computer that powered the site caught fire here. And our team at Johns, literally, our team at Johns Hopkins unbelievably built us a new web server in 8 hours, thus getting the project back online. In this time, we received 20,000 emails from people, most of which said, did you know your computer is broken? But it was very successful. Let me give you some scales. The largest professional classification when we started was Fukugita et al. 3 people, 3,000 galaxies each. I have to confess, we tried the easy way. We did give the problem to a graduate student. His name's Kevin Stravinsky. He's now a postdoc at Yale, having decided that the Atlantic Ocean between us and him is a good idea. But we're trying to name the unit of galaxy classification after Kevin, because he did 50,000 in a month. So the Kevin month is there. Incidentally, the first result in Kevin's thesis was that a graduate student will look at 50,000 galaxies before telling you where you can stick the other 950,000. Anyway, you can see we were doing a ridiculous number of classifications, and this carried on. We didn't quite maintain this pace, but in the first 2 years of the project, we had 250,000 people and more than 100 million classifications. And because that means that many people have looked at each galaxy, we can take an average, we can listen to the majority, we can do things weighting users depending on their behavior, how well they do compared to professionals, to each other. And instead of just having 1 million galaxies, we now have different pots. I have elliptical galaxies, I have spirals with clockwise, I have spirals with arms going one way. The direction of arms tells you about the rotation of the galaxy. So all of these rotate clockwise. All of these rotate anti-clockwise. We've got edge-on spirals where you're looking along the disk. We've got some alien spacecraft, and we've got mergers there in the middle. They're not really alien spacecraft. I said that in a talk the other day, and I was submerged at the end by people wanting to know how they got their hands on this data. So the point is that this works. And we were able to classify our galaxies. So let me tell you about some of the things we've done with that. The first thing is that we were able to show quite how important it was that this was done by eye. Because looking at these these are typical examples of their class. Typical spiral, typical elliptical. And they're almost stereotypical. Because if you ask an astronomer to describe a typical elliptical galaxy, the stereotype is that they're old, red, and dead. The stars in them are old. There's very little star formation going on. Wherever you see blue stars in an astronomical image, you're looking at massive stars that are quite short-lived. So we know that there was star formation here in the last couple of 100 million years or so, because the blue stars are still there. In the elliptical, they've all died out. There's very little gas, so very little star formation going on. So some had argued that you should just split galaxies by colour. Let's just have blue galaxies and red galaxies. That will be the same as spiral and elliptical. You don't need to look at them. You don't need to put anything on the web. But the first thing we showed is that that's actually not true. For example, on the top here, you've got a typical blue spiral galaxy from Hubble, and they're different galaxies, but an example from Hubble, an example from Galaxy Zoo. On the right, you've got typical ellipticals, Hubble and Galaxy Zoo. And in the middle, you've got an example of a spiral galaxy. There are clear spiral arms there, but the colour is the same as the elliptical. We find a whole series of spiral galaxies. And in some environments, they account for about a third of the galaxy population, which are spirals where the star formation has been turned off. In fact, they seem to have undergone a process which, remember, we're not allowed to name things, has the technical term of gentle strangulation. Because what's happened is that these galaxies form in the middle of nowhere, out in the field, less dense regions of the universe, and have dropped into the environment of a galaxy cluster, encountered denser material which has stripped away the fuel they need to keep star formation going. Now, that story was known, but what people didn't realize was this process happens so gently that the spiral arms are left intact. And so now we have a challenge to the simulators. They have to make this process happen, but without disturbing the galaxies. Later on, these galaxies will probably plunge into the center of a galaxy cluster, a much more dense region, at which point they'll collide and form an elliptical. So we don't see any red spirals in the center of galaxy clusters, because by then they've had a much more violent encounter. Speaking of spirals, the first thing we tried to do was supposed to be a sanity check. To show that our data was acceptable. So we have these two types of spiral, clockwise and anti-clockwise. And there was a paper by Michael Longo of University of Michigan, and Michael Longo is a wonderful bloke, but one of those people, if you gave him a baseball bat and a beehive, it would be a matter of seconds before he applied one to the other, just to see what would happen. So he published a very controversial paper, which claimed that he'd looked at 3,000 spiral galaxies, and he found more anti-clockwise spirals than clockwise, to some degree of statistical significance. And this, it's hard to explain quite how controversial this result is. For starters, it's an observation that depends on your position in the universe. If you travel, imagine all galaxies, to me, appeared anti-clockwise. Then if I was on the other side looking back, they would all appear clockwise. And we assume in cosmology that any observation we make on the large scale doesn't depend on your position in the universe. So there's that problem. Secondly, you've got the problem of how galaxies separated by many, many, many billions, in some cases a couple of billion light years, know that on average they're all supposed to go anti-clockwise. When we started talking to theorists about explanations for this, and the kind of thing they would turn around and say is, well, that makes perfect sense if the universe is small and shaped like a donut, or if there's a universal magnetic field that we've ignored until now. It was a really nasty, horrible result. So we thought that all that had happened was Longo hadn't looked at enough galaxies. If you think a coin is slightly biased, tossing 3,000 times might not be enough to tell you whether it's really getting 50-50 heads and tails or whether something else is going on. We had 250,000 spiral galaxies at the end. So we thought we could make this result go away. And to our absolute horror, we found to something like 8 sigma that 52% of our sample were this and 48% this. It doesn't sound like a big difference, but with that many galaxies, it was a hugely significant result, which worried us. And we thought we should be careful. So we put mirror images into the database without telling anyone. And so if the result is real, what you should now expect is more clockwise galaxies than anti-clockwise. And we don't. We still see 52% anti-clockwise and 48% anti-clockwise. It's not, the problem isn't in the stars, but in ourselves. It's us that's odd. There's something about human perception that makes you more confident about seeing spiral arms if they look like this than if they look like this. And it turns out that this is almost a well-known psychological effect, or at least it is with moving images. So I have an example. This is known as the Ballerina Illusion. How many of you see her rotating clockwise? Peer pressure is a wonderful thing. How many see her going anti-clockwise? Few brave souls. How many have seen her switch in the time? Good, excellent. So, if you take a lot of people and a lot of time, you see there's a over a lot of time, there's a preferred direction in the population as to which way this ballerina is spinning. Apparently, if you know about ballet, it's absolutely obvious. But you assume no one knows anything about ballet. And we think we've got the static equivalent here. There's something about the perception of movement in these things. People are interpreting them as spiraling down into the screen there. So we're now writing a psychology paper on this effect, because we have a really large sample of unbiased data. We're even looking to see whether it's different in cultures that read right to left, as opposed to left to right. It's a beautiful spin-off project, and it's produced useful science as well. So I talked about red ellipticals, so I talked about red spirals. Thought I should talk about my own piece of this research, which is to look at the opposite, blue ellipticals, because ellipticals present a fundamental challenge to the model. We think that galaxies build up by the addition of small blocks. If you look right back, as the Hubble Space Telescope has done to the beginning, we see small, faint, gas-rich galaxies, maybe 1/100th of the size typically of the Milky Way. And over time, we expect these to merge together so that you build bigger and bigger galaxies. And so you'd predict from this simple model that the biggest galaxies would be forming today, because you've got to add together many, many blocks, have many more mergers. And the biggest galaxies are ellipticals, but what we actually see is that most ellipticals formed in the early universe. So this is an example of something that we just don't understand. What we wanted to do, therefore, is find the stragglers, the few ellipticals that are still forming stars today, study the process locally, and use that to interpret what's going on in the early universe. So we have a sample now of blue ellipticals. Remember, blue means star formation. So each of these is forming stars at something like 1 to 50 solar masses of gas converted into stars per year. And a typical spiral galaxy like the Milky Way forms about 1 sun's worth of gas into stars per year. So we have our sample. We went to measure the amount of fuel they have for star formation using this place. This is the IRAM 30-meter telescope in Spain. I promise it's a great observing site. The fact it's in a ski resort in the Sierra Nevada has got nothing to do with the choice to go there. But this is capable of looking at carbon monoxide, the second most common gas in these galaxies. And we get something interesting. I know it's a technical graph. This is my work. You can put up with it for a minute, and then I'll move back to more general things. So for each of these galaxies, we have the time since recent star formation began on a logarithmic scale. And we've got the amount of molecular gas, the fuel for star formation. And at 200 million years after the beginning, you see there's a sudden drop. We don't see any galaxies with substantial amounts of gas after this point. And 200 million years is interesting because this is the point at which the black hole at the center of these galaxies begins to have a say in proceedings. We know that there are black holes at the center of most massive galaxies. The one at the center of the Milky Way is about 2 million times the mass of the Sun. We know that in the Milky Way's case because we can watch things orbit it. This is a real image of stars at the center of the Milky Way, observed over the course of about 10 years. And you can see that they're all orbiting, and it's an amazing technical achievement to be able to see this. But you can see they're all orbiting something that appears to be here. And because we know the mass of the stars, we can calculate the mass of the invisible object at the center. Just in the same way we can calculate the mass of the sun by looking at the behavior of the planets. So we know there's a black hole at the center of the Milky Way, and ours is pretty much quiescent. You don't see any light coming from it. There isn't a large amount of material currently falling into it. But it turns out that black holes are polite creatures and have a maximum rate at which they like to feed. And if you try and force material onto a black hole much faster than this critical limit, it will build up into a disk, an accretion disk, and then all sorts of other phenomena happen. And in particular, you can get large jets. So this is the large elliptical galaxy M87, and we've zoomed in on the center, and you can see this is in the radio. You can see a jet coming out from the environment around the black hole at the center. And these jets can have a profound effect on their environment. In our case of our blue ellipticals, we think they heat up or expel the gas, the fuel for star formation, switching off the formation of the galaxy. And we think this process, has long been suggested that this process has a crucial role in the early universe. We've never been able to see it happening. Now, with this local population of galaxies, we can study in detail what happens when a black hole turns on in a star-forming elliptical galaxy. Another place where we're interested in black holes is probably our poster child, our most famous object. Because one of the amazing things about this project has been that people have been willing to get involved not just in clicking on galaxies and answering the questions we ask, but in doing their own research. The simplest way to do that is to find something unusual. And this object is a good example. If I ask a computer to classify this galaxy, it will tell me that it's a spiral. It doesn't show up very well, but there are dust-enshrouded spiral arms here, and move on. If you show this to a person, they start muttering about Kermit the Frog or whatever else you happen to see down here. In fact, the first person to see this was a Dutch school teacher called Hanny van Akel, and she emailed us about it, describing it as a voorwerp. Does anyone speak Dutch? Excellent, my pronunciation was spot on. Voorwerp, we thought, was a technical term, so we called it Hanny's voorwerp. It turns out to roughly translate as thingy. But I'm proud to say that we now have this object in the scientific literature as Hanny's voorwerp. Our big challenge now is we need to find more than one of them, because I want to get the plural, which is voorwerpen, into the jargon. But we haven't. This is a unique object, and it's a bit of a detective story. Hanny told us we didn't know what this object was. We phoned some friends who were on an observing run in a telescope in La Palma, the William Herschel telescope, which is UK run. They have to calibrate their camera and their spectrograph at the start of every night. So they accidentally pointed the telescope at this patch of sky to do the calibration. It was a remarkable coincidence, shall we say. That gave us our first data, and that data told us that this is a blob of gas at about 15,000 Kelvin, so reasonably hot, which wouldn't be that mysterious, except that we also found out there are no stars in this object, no source of heating or ionization. So we were trying to work out why this blob of gas should be so hot. In fact, we now know there's a whole load of cold gas out here, and it's only this blob that's shining. The culprit isn't here. The obvious suspect is still on the scene. There's this galaxy here. If this has a black hole in the center, and it probably does, if that black hole was active, you might expect a jet to come out in this sort of direction, and that jet to be powerful enough to ionize and heat this gas. It's a simple enough story. To confirm it and to get our prosecution of the culprit, all we had to do was look at this galaxy in the X-rays, a typical sign of black hole activity, which can't be hidden by the dust in the galaxy, is X-ray radiation. And so we pointed an X-ray telescope on the Swift satellite at this object for 5,000 seconds, which is quite a lot for one of these observations. And we got 3 photons in total. In other words, no detection at all. So the black hole isn't active. What we think we've got here is a galaxy in the act of switching from being an active galaxy to a quiet one like the Milky Way. We know this happens because we see the population of galaxies change over time. We see that there were more active galaxies in the past, but we've never been able to catch one in the act, and we think that's what we've got here, and we have Hubble Space Telescope time to go and look at this object. I can't resist showing a more recent example as well. Lots of these things come to us through our forum, where about 15,000 people discuss what they've found. I know this doesn't look like much, but this is an example of an object that our users called a Galaxy Zoo P, because it's small, round, and green. There was a whole thread on a discussion on the forum in which people made terrible puns about Ps. And then the rule became that in order to participate in this exciting game, you had to find one of these in the background of a galaxy that you were classifying. And eventually they had a few hundred of them and asked us what they were. We didn't know, we were busy. At which point a group of our users, none of whom had scientific training, went deeper into the data. We provide access, once you've classified a galaxy, to the professional data, just for fun. They looked at spectra, they downloaded the relevant data, they wrote database queries to get the information they needed, and they came to us with essentially what was a pretty good fourth-year astronomy project, better than lots of the stuff I've seen from undergraduates here, announcing the discovery of this new class of galaxy. We followed it up, we've published the paper with them as co-authors, and we've discovered that these are the sites of the most active star formation in the local universe. This galaxy is converting almost all of its gas very suddenly into stars. So we have this interesting population of galaxies that we don't understand at all. When you look at them with the Hubble Space Telescope, a few of them happen to be in the background of Hubble images. Lots of them look a bit like they might be merging, particularly these two at the top. But we don't know if that's a coincidence. We don't know if that's structure we're picking up. It's very, very tricky. But the point is that we have these Ps have been in the data sets since the 60s. But no one looked at them, so no one noticed how unusual they look. No one had time to go and do the digging through the spectra to see if they were really interesting. And we've now got a whole army of volunteers who will do those things for us. And this is happening again and again. We said naively that we didn't care about irregular galaxies, the blobby ones that don't have... They're interesting, but they're a sideshow. A group of users decided that was completely unacceptable and have gone away, and I've got the draft of their paper on elliptical galaxies on my desk. It's perfectly submittable. The top 6 or 7 authors on the paper will be non-scientists. We've discovered this mode of working enables people to contribute by clicking, to move on by discussing in a scientific way what they found, and then even to take part in and run their own research projects. It's very different from the normal model where people get told stuff until the beginning of their PhD, where suddenly they're scientists and can only then contribute. So we're doing further projects. We have Zoo 2, which has got 40 million classifications since February. This is getting to know the galaxies a little better by answering a whole series of questions. We have more detailed images of some of the sky, thanks to repeated visits from Sloan. So just a couple of weeks ago, we switched from images that look like this to more detailed images that show up all sorts of fine structure. But looking ahead, we'd like to continue to involve the public in what we're doing. In fact, we're going to have to. And the thing that keeps me awake at night at the minute looks like this. This is the Large Synoptic Survey Telescope. It's now under construction. I've seen the mirror. LSST is as big as the largest telescopes in the world today. It's about 8.4 meters across, the mirror. But it's designed to do something very different. It will scan the entire sky every 3 nights. Partly to look for things that move, but also to continually build up a deeper and deeper image. So to give you an idea, we're talking about 30 terabytes of data per night. So if any of you are computer savvy, then you'll understand that's a lot. To give you an idea, if I wanted 30 terabytes today, the best and most efficient way for the observatory to send it to me would be to fly somebody over here with a suitcase about this size of hard drives. We don't even know how to handle this data. So let's be sensible. Let's say that all we care about is let's use a computer program to do most of the work and get the computer program to spit out interesting changes that have happened since the last observation. That maybe is more sensible. Well, we think that will trigger 100,000 alerts per night. So what we need is the following. We need a computer program that can do most of the work for us. But it must also not just make a guess at what an object is, but it will need to decide whether that object should be passed to human volunteers for inspection. So it needs to have some sense of whether it's right or wrong and when it's uncertain. The idea is that that will go onto the web. People will look very quickly at the results from this, probably within a few hours, so that anything that's worth following up, they can pick up on. And we're even talking about partnering with some of the global networks of robotic telescopes to enable the volunteers to do the first step of follow-up. So if it's interesting, they can take control of a telescope, go and get the spectrum, go and get measurements in different colors to see how it's behaving, so that we can make use of the data, and so that as professionals we're not overwhelmed. Because what we're looking at is really a flood of data, and we don't have many years to get ready for it. And it's my contention that without involving large numbers of members of the public from around the world, most of this data will be thrown away, and we will miss out on discoveries like the Vorwerp and the Ps, as well as being content with classifying correctly 60 to 70 to 80% of our data. Whereas the interesting things, the blue ellipticals, the red spirals, and whatever their equivalents are, will be lost in the rest of the data. The other thing is that, so this is my idea of how man and machine are going to work together very carefully with this algorithm working with the volunteers. What's interesting, though, is that as we've developed this project, it's become very apparent that it's not just astronomers who are having these nightmares. And so in the next few months, we'll see the launch not of Galaxy Zoo, but of what we've decided with a straight face to call the Zooniverse, a whole universe of zoo projects, which will take, yes, future astronomy projects. We have partnerships with NASA to look at planets. So I don't know how many of you saw the news about water on the moon this week. But the moon is a fascinating place attracting a lot of attention. In fact, the new satellite you can see there, Lunar Reconnaissance Orbiter, it's a NASA satellite that went into its final orbit just a couple of weeks ago. It's sending us 80 gigabytes of image data a day. Again, it's too much. Even if all the world's planetary scientists did nothing but look at the images, they would never be able to see the images at their full resolution. This thing can resolve features on the lunar surface that are about this size. You may have already seen the images of the Apollo landing, where you can see the astronaut footprints. Not individually, but you can see the track. Similar capabilities exist on Mars. This is an avalanche in progress on the Martian surface. There's a slope from left to right. You can see there's a shiny patch of ice here where material is broken off and rumbled downhill. You can see the line of the avalanche and then this dust cloud. Now, watching this sort of dynamic process on another planet tells us a huge amount about how the Martian surface changes over time. But this was only discovered because they happened to print this image out for a public display at some ridiculous resolution and put it up, and somebody was walking along and said, look, it's an avalanche. And then when they looked carefully, there were hundreds of these on the same image. Now, that's one image out of something like 30,000 that have come back from Mars in the last couple of years. Most of the rest haven't even been looked at in this detail. So if we're ever going to do that, if we're going to make serendipitous discoveries, if we're going to classify the craters on the surface of the planets, which give us the age of regions, we're going to need help. So we have NASA involved, and Moon Zoo will launch sometime in the next 6 months, and then we'll move on to other planets. That's probably still astronomy. So we have partnerships, particularly in Oxford. So in the top right, you have two New Caledonian crows. These are famous for being extremely clever. Well, they're Oxford crows, so you might expect that. But in the lab here, they turned out to be able to create tools. They would bend sticks carefully to enable them to break into food containers. It's a nightmare if you're trying to keep these things. But the question is, do they do this in the wild? Or is this learned behavior? They've got as far as, we know that new crows seem to have this ability, newly born crows seem to develop this ability. It's not just learnt from their parents. But obviously in the laboratory setting, you never quite know what they're picking up. If they ever start using Wikipedia, then we'll know they've at least been monitoring. Actually, we'd like them to classify galaxies, because that would make everything very nice. Anyway, the point was, do they do this in the wild? So the researchers a few years ago took a camera, went down to New Zealand, set it up in a forest glade, and sat and sent a student, there's a running theme to this, and sat and watched as the crows travelled across the forest. And they saw crows without sticks. They saw crows carrying sticks. They saw crows hop on into vision carrying a bent stick, but they never saw a crow actually produce the tools. Now they're going back to do a proper effort because cameras have become very cheap. Bandwidth has become very cheap. It's possible to scatter the forest now with cameras. They're even going to attach cameras to some of the crows. But how do you look at that data? You know, a huge amount of effort has been put into face recognition technology and tracking people on CCTV, and it's really hard. The idea that you could do this for crows for a one-off application is far-fetched. Instead, why not spend your breakfast looking at a nice New Zealand forest glade and there's a button if the crow does anything interesting. So we will be working with a whole set of ecology researchers. We have oceanography projects in partnership with the Maritime Museum. One example I like is it turns out that a restriction on the climate models is that most of the data pre-1900 is in the form of ship's logs, which haven't been transcribed. So if anyone fancies sitting at home and reading the journal of a captain sailing the South Pacific, great, please come and do that, but type in every time he mentions the weather. And then that data can actually be used to improve our forecasts of climate change. So we have all of these projects, all of which involve lowering the barrier that people have in participating in research. When we've done a survey, most of our users tell us the major motivation is they want to contribute to research. They're interested in galaxies, sure, but what they want to do is just do something useful with their spare time instead of watching television, primarily. We have a model where you don't need to have gone through formal education to do science. Even just clicking produces a result that ends up in a scientific paper, and we can, I think, produce an active and engaged population of working researchers, whether they're looking at crows, papyri, Mars, the oceans, or heaven forbid, even some galaxies. Thank you very much.